Welcome to another KISSsoft tutorial. Today we're going to talk about the bolt package, the bolt module that's included within the KISSsoft software. You can find it in your KISSsoft software. If you open your KISSsoft, I'm going to open it now. And in examples, bolts and belts, that's belts. We wanted to see hub connections or bolts. Where is it? Connections here. Right there under connections. Right here. And it's this tutorial right here. Tutorial 004E. That's the English version. So first thing, we want to have an idea of exactly what it is we're going to do. So I've got this tutorial open. The bolt calculation according to VDI 2230. And we're going to start out with calculation of a flange connection. So this is a flange connection. You might have this on industrial motors driving something. Who knows what. Anyways, and what we want to do is we want to make sure that the bolted joint's going to withstand the torque and axial forces, etc. So we have some basic information initially, and we can go ahead and start populating the bolt basic data. First thing we're going to do is this isn't a single bolt under axial load. This is a flange connection with torque and forces. Okay, and from the initial data, we have 12 bolts. They give us the pitch diameter, which is 258. They give us the axial force max and min, which is 10 kilonewtons for the upper and 0 on the lower, so we put 10,000 newtons in, and we get a torque of 13,000 newton meters. Additionally, they say we're going to use a hexagon-headed bolt with a shank. So if we drop down in here on the bolt data, the bolt type, this is what we're using. Hexagon head screw with shank. We're going to have a surface roughness. Well, there's a couple things that we need to also put on here. We know that this is going to be a through bolt and it's going to have a nut. We also know that we have a coefficient of friction that's also given to us, which is 0.15. Would be a clean. If you're not sure exactly what to use, you can go to your information icon here and you can look at your approximate values. In this case, we're saying it's going to be a steel on steel clean joint. It'll be dry, so 0.15. Okay, and that's the bolt and the head screw and surface roughness of the thread and of the head support. So we put that information in. We know there's going to be a nut. We know there's going to be a washer under the bolt head, and there's going to be a washer under the nut. At this point, we can probably size. We can size this reference diameter, which is going to be your bolt diameter. This is in metric, so we size this, and you're always going to get this sizing according to proposed, maybe too big in diameter. It says 24, right? Well, one of the things we didn't do is we didn't enter the class, which is 10.9, and that's an ISO. You can also enter in the SAE grade to, grade 5, 6, 8, whatever. This is an ISO based on ISO standard. Now if we size this, it goes to 22. Now, in this tutorial, we have decided that 22 is too large, and you can manually enter your own reference diameter. In this case, we want to enter 16 millimeters. Okay? In our experience, we know that 22 is pretty big. It's going to be too big. In this case, we're going to put 16, and we're going to go with that. So next, we define the nut. We toggle the nut is on because we're going to have it's going to be a through bolt on 2 plates, and we're going to have a nut on the opposite side. We want C45. Now this information up here We're going to leave this default. This information, this external diameter, inner diameter, and height, is not going to update until you go ahead and click C45.1. So the program says, well, I haven't seen anything happen here, but when I click it, it automatically populates this. Okay? And the same thing is true for the washer under the bolt head. I want an RZ16, and it populates it. And the same for under the nut. RZ16, I select it, and it automatically populates this from the standard. Okay? We know that we're going to have a torque wrench because we were told that initially in the information we were provided. Tightening with a torque wrench, right here. See? And we know some other information. We have thickness flange, we have flange surface N7, N8, and we have some flange R diameter. We need to enter this information as well. And we have the inner bore. We need to enter that information. So we go back to KISSsoft, and now we go to the clamp parts section. And it's going to come up and say, based on what we have, it says segment of annulus is strongly recommended. So, and that is what we want, is a segment of annulus. What this basically is doing is it's setting up our geometry to be that flange joint. So we know that we have a, the information provided us is 320 millimeter outside diameter for the flange and a inner diameter of 210. That would be the bore. We hit OK. Now this, we have two materials here. We have the right and we have the left. The right, and if you're questioning this, if we look at this information here, this would be the right and the left. Okay. Top is the top is the left. The bottom would be the right. The way that they're looking at this. The bore is already set up. This is for the bolts. That's an automatic. You can put chamfer on that if you want, and that would take it into account in the calculation. So anyways, on this, they've said, well, we have some materials, and the material we have for the top is a cast. It's an ENGL GJL 200. It's a cast iron flake graphite. And they also tell us that I think we wanted to put the tutorial at least tells us we want a surface finish RZ equal to 8. And on the other side we have a 34 chromium nickel molybdenum 6, which is this one, and that one is going to remain a 16. We do have the depths of these. The cast iron side is 22 millimeters, and the steel side is going to be 18 millimeters. Okay? And the permissible pressure, it says here, is 775 and 775. In the tutorial, I think they have a pressure of 800, but I don't think we can change that. Oh, 250. There it is. I grabbed the wrong one. It was the 250, not the 200. So this is going to define what this pressure is for that material. Okay. Now we have this information all kind of put in. Now we can go back and we can size the bolt length because we know what the lengths of our, or the depths of our layers are, right? So now if we go back to basic data, we go ahead and size the bolt length at 65 millimeters, okay? And we can now calculate this, and it gives us an updated graphic here on the right side. We have a bolted joint. We've defined the material on both sides of the hub. You can see the nut is there. We have a washer on both sides, and we have a bolt with a shank right here and a thread. Additionally, we have a yield point, We have safeties with minimum attained pretension force, ensuring it's 12 and gliding is 1.21. We have fatigue failure at 113.21 and the pressures of 155. What we can do at this point is, if we're interested in seeing if, well, maybe we can use a smaller bolt, we could do that by simply changing this to a 14 and then calculating. It's going to say, well, it doesn't want to calculate this. Did anything change here? No, it already automatically updated everything, and it's basically saying that the assembly preload is larger than our permissible preload, so it can't calculate it. So we go back to 16, and we meet our yield point of 1.16. We have a required pretension force of 64,000 newtons and a required tightening torque of 140 newton meters to 225. So this is your plus minus based on your tightening factor of 1 and 1.6. Okay. Now there are some things we can do in the report. We can look at some information, but we can also do some separate graphs. If we can look at the clamping force, right? If that's something that you're interested in. Maybe you have a large FEA you're going to run and you're interested in what these loads should be. We can also look at pretension force, right? Come on. Kind of extend this a little bit. There we go. Okay. So your preload force and your force. We also can look at, we have the bolt. We're pretty limited here on the graphics, but I mean, we have the information you really need for a bolted joint. So let's go ahead and close these. But now let's look at our report. We can generate a report, and we can look at some information here. Okay, at 150. All right. So we generate a report, and we have some results now in the main window. We didn't take into account temperature really. We said that everything's at 20 degrees. We have a standard thread. It's an M16 bolt. You could change it to English if you choose. We have the pitch and that sort of thing. Some information that's kind of interesting and I think something that we need to look at is a tightening factor, which is 1.6, and the minimum tightening factor, which is 1 right here, right? This is what you're going to specify out in your shop floor, your assembly, whatever it might be. You have a load application factor, bolting type of SV1. We should talk about that. In this case, it's SV1. We have the length of a connected solid. This is your load application. Force application. What this is telling you is that there's nothing in between the bolt. It's the two flanges are straight against each other. Coefficient of friction in the thread. Bolt type. And we want to probably look at your segment of annulus is broken out. We have part A, part B, the through thread, right? Washer information, the nut standard, and the results. Preload loss, this would be loss due to friction. You also have your pretension force N, which is 122,000 newtons. Screw force, all the information you really need to calculate the minimum safeties. So if we come down here a little further, you have the maximum and the minimum torque and tighten on the pre-assembly, and then further down you have your summary, which is the yield point should not be exceeded. And that's information you can take. You have safety against sliding. You have safety against shearing. So this is pretty good information. If you know on these joints that you're calculating, you can also do some other stuff on here as far as you know, side force and shearing and that kind of thing, if you needed more information. Now you can see that it's including our graph too that I had up. So that's kind of it with the bolt package. There's other things you can do in here. There's some pretty good examples that you can look at. You can look at single bolts. You can look at multiple bolts. You can adjust your conditions, right? You can change your temperature if you need to. There are some things in the user-specific setting that you can do. If you can calculate temperature dependent. You can look at thermal expansion of washers and see if that's going to be something that that you might have. You also have vibrational stress that you can look at. So, and the coefficient of tensile strength, etc. Pretty simple module. You can get a lot out of it if you're designing joints, or if you're even specifying joints for driving machinery. And hopefully this has been helpful. It's just one of the many modules that KISSsoft offers. If you have questions, you can call KISSsoft USA. Go to their website, KISSsoft, KISSsoft.com, and you can go ahead and request a test license, or you can just go ahead and ask questions or give any of us a call on the website. Appreciate your time. Thanks again.